For decades, the central processing unit was the undisputed core of personal and enterprise computing. Engineered to execute complex logical sequences with absolute minimal latency, the CPU is built to get from point A to B as fast as physically possible. You can think of the CPU as a brilliant polymath professor. If you hand this professor a complex calculus equation, they will solve it rapidly and flawlessly, but they can still only solve one equation at a time. Artificial intelligence workloads present a different mathematical challenge. Training a large language model doesn't require solving a few complex equations. It requires solving billions of simple matrix multiplications simultaneously. You don't need a single polymath. You need an army of factory workers. This physical die illustrates the philosophy of the graphics processing unit. To build that army, chip designers make a strict physical trade-off. A GPU strips away the heavy control logic and large local caches that make CPUs fast at single tasks. In their place, it packs thousands of simple arithmetic logic units. By prioritizing raw mathematical throughput over sequential speed, the GPU transitions the physical silicon from a solo sprinter into a massive parallel grid. This throughput-oriented design provides the hardware foundation necessary to process the trillions of operations required by generative AI. This architectural map shows a processor built on a TSMC 4N process, housing exactly 80 billion transistors. It operates like a planned metropolitan city. Data arrives at the outer memory controllers, passes through the front-end command processors, and is routed into distinct neighborhoods called graphics processing clusters. When an application sends a command to the GPU, that workload enters the front-end API, the city's toll booth. From there, it is funneled into those clusters to be executed. Zooming into a single cluster reveals the internal factory of the GPU, the streaming multiprocessor, or SM. This is where the actual computation happens. Each SM houses instruction buffers, dedicated warp schedulers, and execution cores. To manage this physical space, developers write code in a strict logical hierarchy. They launch a grid of work, which is broken down into smaller blocks. The hardware locks each individual block to a specific SM, ensuring the threads within that block can instantly share local memory. Inside that SM, the block is further divided into warps, or wavefronts. A warp is a squad of exactly 32 threads. Rather than fetching 32 different instructions, the hardware issues a single instruction that all 32 threads execute simultaneously on different pieces of data. This is single instruction multiple threads, or SIMT. Because one control unit is directing 32 distinct workers at the same time, the GPU achieves an increase in power efficiency per watt compared to a traditional CPU. But an army of tens of thousands of cores is useless if it starves. Traditional GDDR6 memory channels, the horizontal highways connecting RAM to the processor, are too narrow to feed data to these cores fast enough, creating a physical bottleneck known as the memory wall. This cross-section illustrates the hardware solution, high bandwidth memory, or HBM3. Instead of placing memory chips side by side on a motherboard, engineers stack the silicon vertically. They punch microscopic elevator shafts, called through-silicon vias, through the layers. By connecting vertically, each HBM stack achieves a 1024-bit interface. This wide bus allows a single GPU to ingest up to 3.35 terabytes of data every single second. Once the data is pulled from the HBM, it moves through a strict hierarchy. It travels to the globally shared L2 cache, gets distributed to the L1 cache inside the individual SMs, and finally rests in the private registers of a specific thread for calculation. Even with HBM, pulling data from main memory takes hundreds of clock cycles. To survive this delay, the GPU uses latency hiding. If one warp stalls waiting for a data fetch, the SM scheduler instantly swaps it out and issues math instructions to a different ready warp. The GPU never actually eliminates memory latency. It defeats it through multitasking. By maintaining a high occupancy of active warps, the hardware ensures the mathematical cores never sit idle while data is in flight. Keeping those cores fed requires moving data constantly across the physical die. This internal routing is handled by the network on chip, and a central crossbar switch, which directs traffic between the memory controllers and the processing clusters. Yet, modern AI models contain hundreds of billions of parameters. That volume of data exceeds the maximum 80 gigabyte capacity of a single GPU's local memory stack. The workloads physically require multiple chips. To bridge them, engineers utilize dedicated high-speed interconnects like NVLink. Operating outside the standard PCIe bus, these traces fire data point-to-point between GPUs at 900 gigabytes per second in both directions. By routing through an NV switch, the hardware allows an entire server of 8 separate GPUs to act as a single compute entity, pooling their memory and dividing the math. For decades, GPU silicon was divided between flexible, programmable CUDA cores and fixed-function hardware, specific physical circuits hardwired solely to draw polygons and render pixels for video games. Fixed-function hardware operates like a custom injection molding machine in a factory. It has zero flexibility, but it produces its one specific shape at an efficient speed. Comparing these side by side reveals the purpose of the tensor core. While a standard programmable core multiplies 2 single numbers together, a tensor core is specialized fixed-function hardware designed specifically to ingest and multiply an entire 4x4 grid of numbers at once. Operating like an industrial stamp, the tensor core performs mixed precision matrix multiplication and accumulation in a single clock cycle. This specific physical design yields floating-point 16 throughput that standard cores could not reach. While general-purpose cores provide the flexibility to run the operating software, the dedication of silicon die space to these specialized tensor cores is a primary enabler of current AI performance. But this architecture possesses a vulnerability. The SIMT model requires all 32 threads in a warp to execute the exact same instruction. If the software contains an if-else statement, a fork in the road, the threads suffer branch divergence. Watch what happens here. The hardware cannot execute 2 different instructions at once. Instead, the threads taking the else path are masked off and idled. The processor runs the if path for half the warp, then loops back to run the else path for the other half, immediately dropping execution efficiency by 50%. To reclaim lost efficiency before data even hits the memory bus, the hardware employs delta color compression. It calculates the difference between adjacent data points and packs the information, maximizing every available byte of bandwidth. This thermal simulation shows the cost of that extreme parallelism. Firing tens of thousands of cores simultaneously requires immense voltage. A single modern data center GPU consumes upwards of 700 watts of total design power, converting electricity into heat. When optimized AI code triggers thousands of tensor cores to execute matrix math at the same microsecond, the chip draws massive transient spikes of current. The power delivery modules must react flawlessly to prevent the silicon from melting. Hardware engineers have largely solved the logic of parallel computation. Today, the limit on AI performance is dictated by the laws of thermodynamics and the physical limits of power delivery. To bypass remaining system bottlenecks, the architecture implements GPUDirect Storage. This eliminates the CPU from the data transfer process. Using direct memory access, the hardware carves a pipeline straight from the system's high-speed NVMe storage drives across the PCIe bus, dumping training data into the GPU's memory. The operation of 80 billion transistors, thousands of tensor cores, and vertical memory stacks in unison creates an industrial-scale compute node. From conversational language models to real-time protein folding, modern technological advancement relies on this physical infrastructure. It is an engine built on parallel logic, massive memory bandwidth, and microsecond latency hiding.